Hello everyone, welcome to the video lecture series on microprocessor and peripheral interface. In previous session we have seen the minimum mode configuration and maximum mode configuration of 8086 processor. In this session we are going to study the read and write burst cycles in case of minimum mode system. So it is the configuration of 8086 in case of minimum mode, and in this diagram we can see the activities of various signals during the read operation. This particular diagram is generally called as the timing diagram. Here first we can observe the clock signal T1, T2, T3, T4. These are the state of this clock signal. Now we'll see how the reading operation is performed, or what is the sequence of read operation for 8086 minimum mode. So here first of all the first step is related with M/IO bar. So first of all, during this T1 state of read machine cycle, 8086 it will first assert this M/IO bar signal. Now this M/IO bar signal is made low for read operation and it is made high, means 1, for memory read. Means if reading is to be performed on memory, this signal will be high, means the signal will be like this. And if the reading is to be performed on IO port, this signal will be low, means this one. Here the point of cross section, here you can observe the point of cross section of M/IO bar signal indicates the time instant at which the M/IO bar signal becomes valid in this machine cycle. Means at this cross section this signal will become valid in the machine cycle. Now in second step you can observe the ALE. This ALE is forced to be high, means the ALE signal is high when the M/IO bar is asserted. This signal acts as STB input, that is strobe input for external latches. So this ALE signal is high when we are having the asserted M/IO bar signal. Now after this the desired address will be sent, and for that purpose what happens, the ALE is high, then the 8086 will send the valid address of either memory location or IO port to be read on the address lines AD0 to AD15 and A16 to A19. So the address is 20-bit address, so AD0 to AD15 and remaining address on A16 to A19 is put on these two lines, means address will be out when ALE is high, and based on this either we have to read the memory or IO, means based on this signal whether it is low or high the address will be put. Now after that the ALE will be pulled down. So when the ALE will pull down, before this address will disappear from this address line, the ALE line will be pulled down. That means this ALE will be made inactive before the address will disappear from this address lines. The address gets latched into the external latches on the low going edge of ALE signal. So as ALE signal goes low, the address will be latched in the external latches. The latched address will continue to appear at the output of external latch 8282. Now after this, in step number 5, the multiplexed address or data bus will be float. Means the 8086 will float this AD0 to AD15 lines. Here you can observe this is floating of these lines so that they can be used in input the data from memory or IO ports. Means these lines can be used to read the memory or IO ports, and for that purpose these lines will be kept in floating state. And at the same time the bus high enable signal is removed and the A19 to A16 lines will be used for sending the status information. Here at the same time you can observe when these are in floating state, here on this A16 to A19 the status signal will be out, and we can observe the data will be in reading mode and the status signal will be out. Now after that the read bar signal, you can observe when the multiplexed address and data line is floating, at the same instant this read bar signal is made low. So this 8086 it will make this read bar signal low during T2 cycle or T2 state, and this read bar signal is used to enable the addressed memory device or the port device. So as read bar will be equals to 0, the address memory or port device will be enabled. Means when this read bar is 0, at that time the memory, either memory or IO device, it will be enabled. When enabled, this device will put its byte of data on the data bus, and here we can observe the data will be put on this multiplexed line. Now these multiplexed line will act as a data lines. Now here we are saying that when the device, memory or IO device is enabled, it will put the data on this data lines or multiplexed address and data lines. But memory requires some time to read the valid data or to output the valid data, and that time required is generally called as memory access time. The memory access time, it should be as short as possible, but practically it is not so much short. And if the memory access time is not short enough, then what will happen? Then the memory cannot put a valid data on the data line immediately after receiving the address and read bar signal. Means memory is receiving the address and read bar signal. When it becomes low, at that time it is expected that the memory should put its data on the data lines, but due to the memory access time, immediately memory is not able to put the data on the data line. And what 808 will do? 8086 it will treat whatever the data available on the data bus, it will treat that as a valid data. And due to this, what happens? Such a garbage is likely to cause the entire program to crash down, and to avoid such type of problems 8086 should wait for the memory to put its valid data on the data bus, and this can be implemented with the help of ready pin. Now in order to make 8086 wait for the memory to put the valid data, we have to make the use of ready input of 8086. When the ready input is high, then 8086 will operate normally. But if ready input is made low at the appropriate instant in a machine cycle, then 8086 will insert one or more wait states. Okay, and then that wait states are inserted between T3 and T4, means before putting the data on data lines, the wait states can be inserted. And an external device may be used to produce the low ready pulse before the rising edge of clock in T state T2. So here, after this, the read operation will be completed. So these are the read machine cycles in case of minimum mode system of 8086. Now we'll see the write machine cycle and the activities performed during the write machine cycle. And if you observe this write machine cycle, there is similarity between read and write machine cycles, means these two machine cycles are very similar, only few changes are there. So first of all, during T1 state, what happens here? During T1 state, 8086 will assert this M-IO bar low for IO and M-IO bar high for the memory operations. At about the same time, it will pull the ALE to high. ALE signal is pulled to the high, and this will enable the address latches. Then the 8086, it will output the bus high enable. This bus high enable signal will be output on this A16 to A19 address lines, means multiplexed address lines. And at the same time, the address is out on AD0 to AD15 and A16 to A19. So address is out at the same time, means once the ALE is high, the bus high signal will be out on this multiplex lines. Along with that, address will be also put on this AD0 to AD15 and A16 to A19 lines. Now here the lines, address lines A16 to A19, this will always be low if a port is to be written, because the port address is always going to be a 16-bit address. Always the port address is 16-bit, and that's why for means when the port is to be written, at that time these lines A16 to A19, it should be low. After some time, here we can observe the ALE output, it will be pulled down, means ALE will become 0. The address gets latched into the external latches. The address which is available on this address lines, it is latched by the external latch. Then 8086, it will remove the address information from this AD0 to AD15, and it will output the desired data on this data bus. Okay, so after this, during T2 state, the data will be put on this AD0 to AD15 multiplexed lines by the 8086. It then asserts write bar signal during T2. Here write bar signal will be made low, and the low write bar signal will turn on the memory or IO port where the data is to be written. So based on this M-IO bar signal, whether it is a memory write or IO write, based on that, here when the write bar signal becomes low, then that memory or IO port will turn on. Then 8086 gives some time for addressed IO port or memory to accept the data from the data bus, and then raises the write bar signal. So after giving sufficient time, the write bar signal will be made high. If the addressed memory or port devices cannot accept the data within the normal machine cycle, then the external hardware can be set up to produce a low ready input. If the ready input is pulled low before or during the T state of T2, means before this T2 ready input will be low, then 8086 will introduce the wait T state after this T3. So after T3 the wait T states will be added by 8086 if the ready input will be low, and that wait state will remain until our ready input will become high. And during this wait T states, the signals on the data bus, address bus and control bus do not change. Means during wait, whatever the signal is present on address, data bus and status pins, that will remain as it is. If the ready input is made high before the end of a wait T state, then 8086 will continue with T4 state as soon as it finish the wait T state. Means after making or finishing wait T state, the 8086 will finish T4 state. If the system is large enough, then it will need the external data buffers. Then the data transmit and receive bar, here this signal data transmit and receive bar is used to decide the direction of data transfer, and for receive this for transmit this is made high. During the write cycle, the 8086 pushes this data transmit oblique R bar high to configure the external data buffers in the transmit mode. Then this DEN bar signal is made low during this T2 state, and by this way the write operation will be performed in case of minimum mode of 8086. So here in this video lecture we have seen the read and write machine cycles in case of minimum mode of 8086 processor. Thank you for watching the video.